My name is Wolfgang Kessling. I'm physicist and climate engineer at Transolar, Germany. We are here at the National University in Singapore at the Department of Architecture. Transolar did the climate engineering for the School of Design number 4 building. We guided the client and the design team through an integral design process to create a high comfort net zero energy building. How is that possible? How is it possible to design for high comfort and low energy? Let us unpack the stories behind the School of Design. Let us talk about the 5 essential elements of the design. Talk about tropical architecture, sun protection, and creating breezeways. How to ventilate for healthy indoor air quality. How to create thermal comfort with elevated airspeed. How to achieve both indoor air quality and thermal comfort with a hybrid cooling system. And as a result, create a high comfortable net zero energy building. Probably the most important innovation we developed for the School of Design is the hybrid cooling system. That enabled high comfortable conditions and at the same time reducing energy demand by 50%, which enabled a net zero energy operation of the building. Climate is the single most important question on all scales, from city planning to urban scale down to the individual architectural project. Singapore just lies north of the equator with tropical, warm and humid conditions all year round. For thermal comfort, sun protection is essential, rain protection is essential, and breeze is always welcome. Tropical architecture is all about designing with these factors in harmony. Now, what makes this School of Design building a tropical university building? Instead of a closed box, the architect Chris Lee designed a porous building with breezeways and boxes on stacked planes to allow prevailing winds crossing the building. The horizontal roof is protecting the south and the north facade. All rooms are orientated to south. East and west facades are well shaded or closed. The oversailing roof is also where the large PV system is installed to harvest the solar energy for the net zero energy building. Here we are at a model of the building which illustrates quite well what I just explained. We see the building, it's aligned east to west with the long facades to the north and to the south. And that oversailing roof protects quite well the south facades against the strong tropical sun. It also creates a good daylight conditions all over the places. So with this passive design, actually internal loads from solar loads are quite well optimized and reduced. The model also quite well shows how the concept of stacked planes and floating boxes was finally architecturally executed. It shows the many open areas which are naturally ventilated, like the social plaza and exhibition space, and it shows also the different boxes which have all that program areas. Studios, a green lab, department places, workshops. And in the upper part we see the studio spaces which most benefit from the hybrid cooling system. Natural ventilation, hybrid cooling and air conditioning actually describe zones with different thermal comfort and different approaches to ventilation. To understand what we designed for at the School of Design, let us have a look on the people's need for thermal comfort and indoor air quality. We are here in the studio spaces and I want to talk about fresh air and indoor air quality. When we use the word air conditioning, we often have a misunderstanding. It sounds like fresh air, but basically air conditioning refers to cool temperature in a space to create comfort. What is often overlooked is that fresh air supply is also essential in the space, and these are different things. Fresh air supply is related to ventilation. In the tropics, as it is so energy demanding to cool and dehumidify spaces, the fresh air is often reduced to the spaces, and as a result, indoor air quality is poor. This is often described as a sick building syndrome. Not the building is sick, but the people inside the building feel unhealthy because of the bad indoor air condition. For health, comfort, and mental performance, continuous fresh air supply is essential. If not, CO2, humidity, volatile organic compounds, and bad smell easily builds up quickly in a space. That's why international standards suggest 25 to 35 cubic meters of fresh air per person, or in densely populated spaces like studio spaces up to 45 cubic meter per person and per hour. And as a rule of thumb, if this is applied to a space, carbon level stays well below 1000 ppm. What is below 1000 is rated as excellent air quality. What is higher than 1400 ppm actually calls for action to improve the indoor air quality. Let us check what is the indoor air quality in this space. The School of Design is well equipped with instruments indicating indoor conditions like 26 degrees air temperature, like 60% relative humidity, and is also indicating the carbon level, which we read here as 465, which is indicating excellent air quality in this space at the moment. It's clear, it's unoccupied, we are just a few persons in a large space. Let's quickly compare this with my instrument. Let's quickly compare with my instrument, which indicates also 490 ppm. So what is essential here in this space, we have excellent indoor air quality and there is no reporting on sick building syndrome in spaces which are hybridly cooled. The most simple and best approach for fresh air ventilation is a single pass system. It's air which comes into the space and then spills over and is not used again, is not returned again. And actually this is a very simple ventilation system. We have straight ducts coming in with the temperate air, and we have some smaller ducts which just bring in the fresh air into the different locations of the studio. What you see, these ducts are pretty small, they are pretty tiny, because they are just designed for bringing in fresh air. They are not designed for cooling. What you also see, there are no return air ducts. So a ventilation system, a single pass ventilation system, which is used in hybrid cooling, is a quite simple approach and a quite simple ventilation system. What you also see on the ceiling is there are no fan coil units, there's no conventional cooling systems. So how is then comfort achieved? How is this place cooled and conditioned for comfort? And the answer for this question lies in some smart bioclimatic design. Let's unpack the science behind thermal comfort and understand how this place is feeling so comfortable. Thermal comfort is actually the state in which a person neither feels too hot nor too feels too cold and just perceives the environment as pleasant. To understand that better, it's a good concept to think about a heat balance between the body heat production and these environmental parameters which help us to cool our body. Let me introduce the 8 key parameters to understand and describe thermal comfort. Then let me introduce the concept of mean radiant temperature to describe radiant comfort, and let me introduce the operative temperature as a strong parameter to describe thermal comfort. 8 parameters. That sounds complicated, but the thing is, human comfort is related to a complex interplay out of these 8 parameters, and we cannot opt out. Humans are sensors, and we interact with our environment through convection, through radiation, through heat conduction, and through sweating. Now, the positive thing out of these 8 parameters is that we have more choices to create thermally pleasant environments. We can compensate higher temperatures with a gentle breeze. We can design a facade for excellent radiant comfort. And that's exactly what happened here at the School of Design. There are 8 important parameters. 2 of them are physiological parameters and describe activity and the clothing of a person. Both parameters cannot be influenced by designers, but people use activity in clothing to adapt to a given thermal environment. The other 6 parameters are physical parameters, and these can be influenced by design. 3 of them are related to radiation, 3 to air. We are most likely more familiar with the 3 physical parameters related to air: air temperature, air humidity, and air speed. These parameters are related to convective heat exchange between the body and the surrounding. Then there are 3 parameters of radiation: shortwave direct solar radiation, shortwave diffuse solar radiation, and infrared radiation, or in other words, heat radiation to the surrounding. These 3 radiant components are summarized to what is called mean radiant temperature. This is a useful concept to describe the radiant exchange between the human body and the surrounding and the human radiant comfort. In practice, radiant temperature is often neglected, yet it is a crucial factor. In an environment without air movement, it's about 50% what the human body feels. This is so relevant that the mean radiant temperature and the air temperature became combined into a parameter which is called the operative temperature. To give you a reference, in the tropical environment with a clothing factor of 0.5, international standards recommend that the operative room temperature is in the range of 24 to max 26 degrees to create a thermally good environment. Let me make an example. If the air temperature in a space is at comfortable, let me say 25 degrees, but the radiant temperature is at 30 degrees, people don't feel comfortable, because what they feel is not air temperature, it is the operative temperature of 27.5 degrees. In this case, the air conditioning temperature typically would be trimmed down to say 20 or 22 degrees to create comfortable operative temperatures in the space of 25 to 26 degrees. So that was a lot of theory about thermal comfort. Let's have a look on something. Let's have a look on the mean radiant temperature in this space. Here I have an instrument which helps us to measure the mean radiant temperature in the space. The temperature of the ceiling, the floor, and the 4 surrounding surfaces. And what I read here is that the radiant temperature is more or less exactly the same as the air temperature. That's confirming already that we are in an environment which is with a very good thermal and very good radiant comfort. Let me bring that instrument closer to the facade. Give it a second. And what we see is, so close to the facade, the mean radiant temperature is roughly 1.5 degrees higher than the air temperature. Again, confirming the excellent radiant comfort in this space. And this is due to 2 facts. We have an excellent glazing, solar heat protecting glazing with solar heat gain coefficients which are quite low, but still giving us good daylight. But it's also because of the oversailing roof we already have talked about. The roof which is protecting the facade against direct solar radiation. And we can see that when we look to the shadow cast by the roof. We can see that the roof casts an excellent shadow and there is no solar gains on the facade. So in summary, what this confirms actually is a design for excellent radiant comfort, which immediately says there's no need for cool air temperatures to compensate for a high radiant environment. Let me check the air temperature in the room again. At the moment, it's something like 27.2 degrees. And that's exactly what we designed for. The reason for these higher temperatures feeling comfortable are actually the ceiling fans in the spaces. They create a gentle breeze. They create something what is technically speaking called elevated airspeed. Let me explain the effect of elevated airspeed. A gentle breeze or fan can make a room feel several degrees cooler without changing the thermostat. At about 1 meter per second airspeed, people typically feel about 3 degrees cooler, reducing the need for air conditioning. The diagram even suggests a slightly higher cooling effect. The exact perception varies from person to person, but this is the typical range. Humans are sensors. We can read the thermal environment through observing other people. Just have a look on the people. Have a look on the activity, the clothing, and the body language. The people look comfortable. If you don't want to change something with your thermal environment, then you are comfortable and pleased with this environment. Air movement is actually quite complex phenomena. What we want to have is a gentle breeze, something like 0.7, maximum 1 meter per second, to create that cooling effect roughly in the range of 1 degree. How is that air movement created in the space? Before I get to this, how much is 1 meter per second? 1 meter per second is just what I feel at my hands when I walk with this speed. It's not a hurricane. It's just a gentle breeze which cools my body. I'm standing in between two fans. What do these fans do? They move air, they press air down, this air moves through the space and collides in the very center between the two fans, creates an uplift and a large circle like a donut. This is the source of air movement in the spaces. The fan moves the air, and what that pattern looks like, what the fan creates, we will have a look at this. Let me use my little device to illustrate the airflow under the fan and in the space. Let me first go under the fan. So what I see here and what the device shows, there's a strong air movement under the fan. Probably something like 2 meters per second. And now I move out of that so-called fan zone, and I'm just moving 0.5 meter, and what we see, we are in the still air zone. There's no air movement here. Let me move further. Let me move into the very center between the two fans, and just have a look on my little device. It indicates in the very center an uplift. It indicates the air which is colliding between the two fans and lifting up and going through that space. Now, we have the fan zone, we have the still air zone, and we have that zone where the air goes up. What is the interaction with my body? Let me go back into the still air zone and have the device just in front of me. So what I'm now creating I'm a resistant in this airflow. And if I get this device closer to my body, we will see that there is this movement shown by this device, shown actually that the airflow is colliding with my body, creating a gentle breeze, the breeze which cools myself at my body. And this is because I'm the resistant in the space, and wherever I move around, I interact with the airflow of the ceiling fans. We have seen that air temperature alone cannot explain thermal comfort. The 8 parameters, radiant comfort, and elevated airspeed all play a role. Let us use this advanced understanding of thermal comfort and combine this with the role of fresh air. Let us ask the question, what is hybrid cooling, and how are spaces cooled if there is no conventional air conditioning? Hybrid cooling uses fresh air to cool the spaces and to create comfort. Let us look on these principles by comparing the combined cooling effect of fresh air and elevated airspeed and set that into perspective of typical internal heat loads in a space. I will use simplified but indicative numbers for that. Supplying each person with 35 cubic meters of temperate fresh air at 18 degrees already provides effective cooling. As this air warms up by 10 degrees from 18 to 28 degrees, this is equivalent to a sensible cooling capacity of about 120 watts. At typical light activities in a studio, a person produces also about 120 watts of total heat load. About 75 watt of that is sensible heat, about 45 watt is latent heat from perspiration. The latent heat raises the humidity in the air but does not increase the air temperature, as it is carried away in vapor form. The fresh air system is therefore designed to handle up to 120 watt sensible load plus 45 watt of latent load per person. This means that beyond offsetting the person's 75 watt sensible load, the fresh air also provides roughly 45 watts of additional sensible cooling load to the space. So how is comfort achieved? In this example, we allow the air temperature to rise to 28 degrees. On its own, this would not feel comfortable. However, a gentle breeze coming from a ceiling fan lowers the perceived temperature by about 3 degrees, bringing it to about 25, so occupants still experience the space as comfortable. At 4 to 6 square meters per person, this yields about 6 to 10 watts per square meter of sensible cooling. Though modest compared to full air conditioning, it is significant in buildings with efficient envelopes, low solar gains, and reduced loads, as in the School of Design number 4. Cooling can be raised by 30 to 60 watts by lowering supply air temperature by 2 degrees, or raising airflow to 45 cubic meters per hour. In practice, occupancy variations already create this effect. Both strategies are applied at the School of Design 4 during peak periods. In a nutshell, conventional air conditioning cools spaces to low temperatures and low humidities. Hybrid cooling takes another approach. It supplies fresh air at higher rates, at higher temperatures and higher humidity to the spaces. And it uses the fresh air when combined with elevated airspeed to great comfort. So hybrid cooling is less about a technology for higher energy efficiency and more about a technique, an efficient way to create human comfort. And it unlocks 50% energy savings to do so, far more than the incremental increase of 5% energy efficiency gains in conventional systems. With the successful implementation and operation at the School of Design, the hybrid cooling system demonstrated a paradigm shift in comfort design, allowing higher temperatures, being compensated with elevated airspeed, and allowing higher humidities in the space. These principles have since been adopted into the Singaporean Code of Practice. Hybrid cooling is not limited to this project. It can be widely adopted in tropical and subtropical climates. It can be adopted in schools, in university, and office building, in all applications where high fresh air rates are needed. This brings us back to the origin of the story. The Department of Architecture was seeking a high comfort net zero energy building. What is a net zero energy building? A useful definition is when all the energy which is required to operate the building is produced at the site itself. For instance, on a roof with a PV system. This definition is also quite useful for the context of the building industry because it informs the involved architects, client, and all the involved contractors about actions in their context, in the context of the traditional boundary of the building itself. Why are not all buildings designed for net zero? What are the challenges? To answer this, let us first look at the potential of renewable energy production and compare it with the building energy demand. In Singapore, solar radiation on a horizontal surface is about 1700 kilowatt hours per square meter in year. This represents the renewable energy potential of the site. Considering the efficiency range of photovoltaic systems, the typical electrical output is around 260 kilowatt hours per square meter in year. In other words, this is the given annual energy budget, what 1 square meter of roof at the School of Design can produce. Now let's compare that with the demand. 10 years ago, a typical office building had an average energy use of about 250 kilowatt hours per square meter in year. So, in a nutshell, 1 square meter of roof can just about supply 1 square meter of office space. Put it differently, if energy demand is that high, a net zero energy building could only be a single-story building. So, it is essential to reduce energy demand first and optimize the building. For the School of Design 4, the overall energy use intensity was reduced to about less than 70 kilowatt hours per year. That enabled that the multi-story building can be operated as a net zero energy building. How did we create a net zero energy story? Together with the client, the architect, and the specialist designers, the team conducted a series of design charrettes. We started with establishing the maximum energy budget at the site and comparing that to the energy demand of a typical university building. This large performance gap made it clear to all involved that energy demand seriously needed to be reduced. Each charrette then focused on a key topic: improving the envelope and the facade performance, introducing high-efficient air conditioning systems, transitioning to hybrid cooling and reducing user-related energy demand, optimizing multiple aspects of the design and verifying design decisions with building simulations to guide design decisions. This process, finally, reduced the energy demand by a factor of 4, with the introduction of the hybrid cooling as the central strategy. Let's bring it all together. We have seen that thermal comfort is not just about lowering the air temperature. It's about radiant aspects, it's about elevated airspeed, it is about air humidity, and above all, it's about fresh air supply. We also have seen that hybrid cooling changes the rules. It's not about supplying cooler supply air temperature to the space. It's about using temperate air supply, elevated airspeed, and a smarter definition for thermal comfort. And as a result, indoor air quality is better, the transition between inside and outside feels way more natural, and energy required is reduced by 50%. So, what we also have seen, that this is essential for the net zero energy, which is not magic. Net zero energy is about maths. It's about using the energy budget which is provided by the sun to operate the building. And if we don't reduce the energy demand of our building, no PV system will be ever enough. But if we establish an integral design process, optimizing the building, optimizing the facade, and using hybrid cooling, we can operate our building in the tropics within this given frame of energy and create a net zero energy building. And we have seen that this is not theory. School of Design is the proof. It works. It is built. It is operating. And it has even shaped the building code of Singapore. So the message of this building is clear. Comfort and sustainability are not opposites. They belong together. As designers, we have the tools, we have the science, and we have the responsibility. The future of building is not about doing a little less harm. It is about creating places that are healthy, inspiring, and climate positive. And all within the energy that the sun gives us every day.